Welcome back to the Deep Dive. You send us your sources on rock fracture mechanics, and we've gone through them, the papers, the equations, all of it. Our mission today is to give you the ultimate shortcut to understanding how engineers are solving one of the oldest problems in construction, predicting how brittle materials like rock and concrete actually fail.
And we're talking about everything from, ancient Roman concrete to the rock foundations under modern skyscrapers. All these materials have the same Achilles heel. They're incredibly strong if you push on them, great in compression.
But they're terribly weak when you pull them apart. Tension.
Exactly. And that weakness led to some major miscalculations historically. Engineers were using classical theories like the Moore-Coulomb criterion, which assumed something that just wasn't true.
That the material was perfect, flawless.
Right, and that whole illusion of perfection was shattered way back in the 1920s. Researchers working with glass figured out that in the real world, no material is perfect. Every single structure has tiny inherent flaws.
And that realization gave birth to modern fracture mechanics. But even that field hit a roadblock, didn't it, around the 1960s?
It did, and this is where it gets really tricky for engineers. They found that key material properties, like fracture toughness, weren't constant. For materials like concrete, they were actually size-dependent.
Which is a huge problem. I mean, you need a property to be consistent whether you're testing a tiny sample or a massive bridge component.
Precisely. If the toughness changes between a small lab specimen and a giant dam, your safety factors are basically just a guess.
So what was causing this scaling issue?
It's because these materials exhibit what we call quasi-brittle failure. It's less like a clean snap and more like paring a piece of heavy fabric. Right before the main crack fails, a whole cloud of microscopic damage forms right at the tip. We call it the fracture process zone, or FPZ.
Okay, so it's like a soft damage buffer zone.
That's a perfect way to put it. This FPZ blunts the crack, it spreads the stress out, and that makes the whole failure process nonlinear. Catastrophic failure only happens after that zone has grown enough.
And because that zone size relative to the whole sample changes, the toughness appeared to change.
Exactly. Which brings us to our mission for this deep dive. We're looking at a huge breakthrough, a streamlined testing system called the peak load method. It's designed to find those essential size-independent fracture properties.
And it does this using new, really compact cube and disc specimens, eliminating the need for a lot of complex, expensive lab gear. Okay, let's get into that. So traditional theory, linear elastic fracture mechanics, or LEFM, assumes a perfectly sharp crack. But the moment you have that FPZ, that cloud of microcracks, LEFM, just doesn't work anymore.
Right. That's why for rock and concrete, you need nonlinear fracture models, NFMs. And here's the key difference. NFMs almost always need at least two quantities to describe the failure, not just one.
So you're not just measuring the force to break it, but also the material's internal resistance to that damage growing.
You've got it. And two models really lead the pack here. First is the two-parameter model, or TPM.
And that's designed to predict the final unstable failure point.
Yes. It uses two things. First, the unstable fracture toughness, which we call KICS, that's the stress intensity right at the peak load. And second, the critical crack tip opening displacement, or CTODC. That's a physical measurement of how much the crack has been blunted by the FPZ.
I see. So the TPM describes the end game. What about the other one, the double K model?
The double K model describes the whole process. It uses an initiation toughness, the force to get the crack moving, and an unstable toughness for when it finally fails. And what's interesting is that the research shows the unstable toughness from both models. They're statistically the same thing. They measure the same physical limit.
And that limit, that peak load, is the critical moment. When you plot the load versus the actual opening of the crack, you see three distinct stages.
You do. Stage 1 is linear. The material is just stretching. Stage 2 is where it gets interesting. That's stable crack growth. The curve goes nonlinear because that FPZ is forming, it's growing, it's soaking up energy.
And only after you hit that absolute peak load, PC, you get to stage 3.
Catastrophic, unstable failure. Yeah. Exactly.
Understanding that stable growth phase is what made old testing so complex, but it also inspired these new specimen designs. We're moving from traditional beams to these compact discs and cubes, the SNDB and SNCB.
And the innovation there is just accessibility. If you're an engineer in the field, you're not cutting huge beams from a rock face. You're drilling cylindrical core samples.
Right. And these new shapes can be made directly from those standard cores. They're compact, they're light, way more efficient for field work.
Totally.
Okay, let's get to the methodology. If the gold standard requires tracking every tiny bit of deformation, How did they prove that a much simpler method, the peak load method, is just as good?
First, you have to appreciate how complex that gold standard is. It's the RILEM compliance technique used for concrete. To do it, you need extremely sophisticated and expensive equipment. Specifically, a machine with CMOD control crack, mouth opening displacement control.
So I need this special machine just to measure, millimeter by millimeter, how the crack is opening as the rock fails. Why? What's that data for?
You need it to capture that whole nonlinear stable growth phase. You have to track the entire load CMOD curve right up to the peak. Then you use that data to calculate the Young's modulus, the critical crack depth. It's a whole multi-step curve fitting process.
It sounds like a specialized lab procedure, not something you'd run on every construction site. So how does the peak load method just skip all that?
This is the genius of it. Instead of measuring the crack's movement, you only need one number, the ultimate peak load, PSC. You test at least 3 specimens, each with a slightly different pre-cut notch depth, and you just record the maximum load each one took. That's it.
Wait, so you skip tracking the crack extension entirely. How can you possibly figure out those 2 non-linear parameters, the toughness and the displacement, without measuring the displacement?
Because they treat the test backwards. They use computation instead of physical measurement. They treat those 2 parameters, KICS and CTODC, as the unknowns in a system of equations from the 2-parameter model.
I see. So you have 3 knowns, the 3 peak loads you measured, but only 2 unknowns, the material properties. It's an overdetermined system.
Exactly. And you solve it with an optimization approach. You're essentially looking for the pair of material properties that best fits all 3 of your simple peak load tests.
That's a fundamental shift. You're replacing expensive hardware with simple math. But the big question is the simple test just as accurate?
And that's what the validation proved.
Which brings us to the first case study, Ankara andesite rock, using those disc-shaped or SNDB specimens.
Right. So first they ran the traditional complex compliance method to set a benchmark. They found a stiffness, a Young's modulus, of about 17.8 GPa, and the unstable toughness was around 1.3. And critically, the variability in those results was very low, well below the 20% threshold considered acceptable. So they had a really solid target.
Okay, so a reliable but expensive benchmark. How did the simple peak load method compare?
They did a rigorous statistical comparison. They used a student's t-test, which compares the averages, and an f-test, which compares the variability or the spread of results, and they focused the comparison on the initiation fracture toughness.
Why that specific parameter?
Because it's derived mathematically from both of the other main parameters. It's a synthesized value, so it makes it the most robust point of comparison for the entire methodology.
So what does stats say? Did the simple method hold up?
It held up perfectly. The calculated values for both tests were so small that statistically you have to conclude they're measuring the exact same thing. The differences were insignificant.
So the difference is basically just random noise, not a flaw in the simpler approach.
That's it. And to really confirm it, they measured the practical importance, the effect size, using something called Hedges dye. It was found to be negligible, less than 0.10. So the conclusion is clear. There is no significant statistical or practical difference between the 2 methods. The simple one is just as precise.
That is a huge win for engineers. So once the method was validated, they moved on to the next question. Can we reliably use these new compact shapes? This takes us to case study 2 with a Lasik limestone.
This was a high-quality limestone, very strong, and they compared traditional rectangular beam specimens against these new single-notch cube bending or SNCB specimens cubes, about 71 millimeters on a side.
So the classic beam versus the new cube, what did the peak load method tell them?
The unstable fracture toughness values were nearly identical. The beams gave 2.260 and the cubes gave 2.244. The difference is tiny. This confirms that these are true material properties. You can reliably determine them using these new compact shapes.
That's the whole point, isn't it? A material property shouldn't depend on the sample's shape.
Absolutely. Though they did find one subtle difference, which actually helps validate the model. They called it the deep beam effect.
Okay, tell me about that. Why does a cube break differently than a long beam?
Well, a standard beam has a fairly small compression zone at the top when you bend it, but the cube is so deep relative to its span that it behaves like a deep beam. The compression zone is much larger, and because of that, the physical crack extension was actually smaller for the beams than for the cubes.
I see. So the way it fails, how far the crack runs, depends on the geometry.
Yeah.
But the critical properties that define the failure don't.
That is the key takeaway. The fracture parameters are consistent. The SNCB cube is a robust, practical alternative.
So what does this all mean for you if you need to stay ahead of the curve in structural engineering?
It means there's now a clear, validated path to characterize these materials efficiently. Engineers can use these compact, easily made samples, the SNDB and SNCB, and rely only on simple peak load data. You don't need to spend a fortune on specialized equipment to track the CMOD curve.
And that shift from complex physical measurement to computational optimization is really the story. The researchers also made sure the computational tools were accessible, right?
Correct. They showed that a much simpler numerical technique, the crack closure integral, or CCI, gives consistent results. And it works even with the common, less sophisticated 8-node solid elements.
Which is important because those are the standard building blocks in popular engineering software, like SAP 2000. It connects this advanced theory directly to the tools engineers are already using.
It's the final piece of the puzzle. It marries the theory with everyday practice.
Which brings us to our final thought for this deep dive. This research proves that a really complex problem in structural integrity can be solved using minimal input, just a few peak load numbers, without sacrificing any accuracy, as long as the underlying equations are solid.
And if we can simplify rock mechanics testing this much, what other, complex multi-parameter problems in engineering might yield to a similar simplified peak load-like approach?
Something to think about next time you consider the ground beneath your feet. And that's all for this deep dive. We'll see you next time.